So now that we have Phenix and Coot, we're going to use these programs to start learning how to refine structures. How are we going to do that? We're going to access this link and then download this entire folder. And then we're going to open this up and essentially extract this, extract all. We're going to call it by the PDB code 4LDJ, extract. And inside of this, we're going to change the inside folder also to 4LDJ. Say OK. And then if we go into this folder, we see clearly that we have our sequence data, our electron density map data, the solved structure, and then practice structure that we can improve and fix. So all we're going to do is go ahead and click dash. And then we're going to cd out of this, and then we're going to copy recursively the 4LDJ folder. And where do we want to copy that? We want to copy into our root directory. Remember our Phenix folder that we set up? We're going to make a new folder inside of the Phenix folder, and we're going to call that folder projects. And we say enter. Now if we cd into the projects folder, there should be 4LDJ, and if we cd into this folder, it's going to provide us with all the items that we copied over. Okay, with this, now we're going to open up Phenix. So we can go back, cd up into the projects folder and cd up into the Phenix folder, and then type in our sourcing command to say, hey, this is where to find the Phenix startup information, which is this Phenix, and then type tab, and then Phenix environment sh, and now you say Phenix. Then you click OK. Alright, so now that we're here, there's a lot of stuff. All of these sections have sub-processes that you can use to work on your projects. First and foremost, you have to pay attention to which folder or which directory you currently are in. Right now, I'm in the Phenix general directory. I want to browse and go into the projects directory, and specifically the 4LDGA directory. I click open. While I'm in this directory, I want to create a new project, so I click new project. I say 4LDJ, and where do I want my project to be? Not in the regular Phenix folder, but inside of the projects 4LDJ folder. We see the project ID is correct, the project directory is correct, and we say OK. Now we have to just double check that the correct project is selected. If we selected this project, then we see the directory changes. If we select our correct project, then directory goes to the correct project directory. Why is this important? Any new files created when you're doing any refinement or model building goes specifically into that specific project folder. That's why it's important, so that all of the information for each entry is sort of separated from each other. So we can go ahead and click refinement. Phenix refine is very important. If you can refine a structure and then go into Coot, modify it, fix it up a little bit, and then put into Phenix refine again, this iterative process is very important and essential for solving protein structures. So we can click Phenix refine. And then we can say add file, and inside of our 4LDJ project folder, we're going to add the MTZ file, or the electron density map, the practice file, and also the sequence file. So electron density map, the sequence file, or the sequence of the amino acids, and then the structure for practicing and improving. Alright, we see all of our data is here. From our MTZ file, the space group and the unit cell were imported. Data labels, this is the only one we have, the FP, SIG-FP, and then our free label. This is also the only one that we have. We can click refinement settings. We can just leave all the settings the way they are right now and go ahead and click run locally. And as soon as it starts, you will see new tabs showing up, and also this idle will also change. And while it is working, Coot will also open up so you can see things happening in real time. The running process takes on average around 10 to 16 minutes. So we can go ahead, speed this process up, and see what happens. You'll see that cycle 1 has initiated. Our work on R3 are extremely high. These are very, very, very bad values. But we will see as the refinement process happens over time, these numbers will decrease significantly to around 0.2 or 0.3. And now I see that our work in R3 have significantly decreased. to around 0.5 and 0.54. The red is the R free, the blue is the R work. Both of them should be very low, and eventually in the process of building, refining, adjusting, and refining, adjusting, and refining, we want to get the R free as close to R work as possible. Because if R free is significantly larger than R work, then that means the structure was oversolved, and that we have to go back in and adjust some things. While the R work and R free does seem a little bit concerning in terms of spiking up right now, it'll eventually come down a little bit better. Now it's decreased significantly to around 0.34, 0.36. That's much, much, much better. And now it is finished. If we want to see where the data is, for example, if we go open another terminal window, let me say cd into our Phenix folder, and then projects folder, and then we say ls. This is cd into for LDJ. And we see the refine folder, which is the new folder that was just produced from Phenix refine. Cd into the refine folder. And now I see all the information. When we want to make any additional modifications in Coot, we're going to use for LDJ refine 001.mtz and also for LDJ refine 001.pdp. So how are we going to do that? Before we individually see it in Coot, the Phenix Refine results also provide a lot of very useful information, especially in terms of what areas that we can focus on and also fix. For example, in the results section, here are all of the output files. The most important is the new refined structure and also the new MTZ. If we wanted to do another second round of refinement, and instead of our original 2 input files, we would now put these 2 files in for the second round of refinement. But say if we wanted to make some additional modification in Coot before we do a second round of refinement, then we make the modifications, save as a new PDB, use a new PDB, and then use this MTZ. But mode property can give a lot of very important information. Its summary, for example, Ramachandra outliers, rotamer outliers, those are things that we can try to improve upon. Here are some basic geometry things. For example, if I just clicked into here, it will bring us to a location that needs help. And also, for example, like another part like this. So you can go through basic geometry, proteins, right, especially this very green and red region. This part definitely needs a lot of help, especially this part. And then clashes, especially when atoms are a little bit too close to each other. This is what you can do to start looking at them and then treating them on a case-by-case basis. Essentially, the Phenix Refine results provide a lot of information to directly lead you to the locations that you need to fix to address these issues. So, for example, if we just want to start with the first amino acid glycine and say apply, now we are at glycine, we can just zoom in. Yes, and just like that, move it in closer. Yeah, definitely want to move these guys over into this space. Yes. Accept. That's odd, this little thing. I don't know what it is, but I'm sure it will be revealed to us very soon. Oh yes, this is a very good one. Let's do rotamers. Click this guy. Yes. There. Oh, this is not good. Rotamers again. That's much better. Yes. And then just go through refining each of these segments one by one. And then when you're happy with all of the ones, and this is just a little demonstration of a couple. And once you feel like you have done enough refinement and fixing up the model according to the green and red areas and filled in all of the blobs and adjusted all of the structures, addressed all of the Ramachandran plot issues, all the red dots, and also have addressed all of the unmodeled blobs, the difference map peaks, when you think you're ready for the next round of refinement and that you've done good enough to move on to the second round, then you can go ahead and save as coordinates, select file name, and then save as your new refined structure. So that when you go back into here and create your new Phenix Refine project for the second round of refinement, you can add your new refinement structure, add in your NTZ file for your first round of refinement. Double check everything, double check the refinement settings, and click on the run button. Now it's finished. And as you can see, even though I only adjusted in Coot 10 amino acids just as example, the R-work and R-free are now significantly lower with the second round of refinement than the original round of refinement, where it was R-work and R-free of around 0.36 or even 0.38. So this is very, very good. It shows that this iterative refinement process works very well in essentially allowing the model to more accurately represent the electron density map. So we want to go ahead and look at our structure and see how it compares now. We can go to chain A and see if anything changed. Zoom in. Wow, now it fits nice and neatly into its electron density map, much better than what it originally was. Disulfide bonds, the sulfurs fit perfectly in the electron density map. All of these look very perfect. This looks great. Looks great. This part got fixed. It originally had a green area, now there's no green left. And just like that, we can make the refinement process in Phenix and then go and make individual small adjustments to make it fit even better and then fully refine the process. And then do this cycling refinement, Coot refinement, several times until the R-free and R-work are as low as possible, up to around 0.2 or lower or even 0.15 or lower. When it gets to that point, the model very strongly represents the electron density map, bringing you closer and closer to the real answer and the real structure of the protein, which can be used for therapeutic drug design.